Good day to you. We're here on location, and we're here today to recreate a famous experiment in the history of physics, the experiment where Galileo dropped cannonballs off the Leaning Tower of Pisa. Now, there's some interesting legends surrounding this experiment. It's unlikely that Galileo actually did drop cannonballs off of the Leaning Tower. Cannonballs had been dropped by other scholars previously, and so Galileo was not the first to do the experiment. And in all likelihood, if cannonballs were dropped off the Tower of Pisa, it was a pupil of Galileo that did it, a fellow named Vincenzo Viviani, who first wrote about this experiment in his memoir of Galileo. Now, Galileo nevertheless deserves credit because he was the first to actually show, with a series of experiments, an explanation for why bodies fell in the way that they did. And in the physics at the time, which had been formulated by Aristotle several thousand years previously, the idea was that motion was divided into two different kinds, so-called natural motion and unnatural motion. And one example of natural motion was the falling of bodies under the influence of gravity. And the theory there was that heavy things tended naturally to find their natural place in the universe, and of course that was down, and this is why bodies that had mass, bulk to them, tended to fall downward towards the earth. They were seeking their natural place. And one of the corollaries of that idea was that heavy things, that is things that had a lot more mass seeking their natural place, would fall faster than bodies that had less mass trying to seek its natural place. And Galileo showed that that's actually incorrect, and he did so again with a combination of experiments, theory, and so forth to build a convincing explanation for why bodies fell the way they did. So we're going to be dropping several things off of a tall building today, and one of the things that we'll be doing is we'll be dropping basketballs of different sizes from the buildings. This is a standard regulation basketball over here, and this is a smaller basketball, about 1/6 the size, and note the major difference in diameter. That's going to be important in our explanation. Then we're also going to be dropping some other balls off of the roof. We're going to be dropping two balls of this size. This is the lacrosse ball, quite solid and massive, and this is a wiffle ball over here, and obviously it's about the same diameter, but it's much different mass. And then we'll be doing another drop of these two balls right here. This is a standard issue golf ball, and this is a so-called golf practice ball over here. We're also going to be making physics fruit salad today, and we're going to be dropping several different kinds of fruit off of the building to see what happens. We'll be dropping some large watermelons here. This is a seedless watermelon. It weighs about 12 pounds or so. This is a mini watermelon. It has about half the weight. It weighs about 5-6 pounds or so. And then in combination of that, we'll also be dropping different fruits that are smaller. For example, we'll be dropping a lemon, and then a cherry tomato, which in this case is kind of beat up a little bit, but we'll be dropping intact ones when we actually do the experiment. So that's the background behind what we'll be doing, and now all we need to do is we need a building to drop the fruits off. The first objects we're going to drop will be the two basketballs of different sizes, and you can see them up there in the window of our insectary here, and on my signal they're going to drop them. Ready? Drop. And what you saw there was that the balls came down at different positions. Part of that was due to being released at slightly different times. And we can correct for that when we analyze the motion a little bit later. The next objects we're going to drop will be the lacrosse ball and the lighter wiffle ball. We'll just wait for the traffic to clear and the wind to die down. Ron, ready? Let it go now. Well, as you can see, they came down at markedly different rates, and we'll see this again and again in the different kinds of objects that we drop. The next objects that we'll drop will be the golf ball and the small wiffle ball. Ready, Ron? Drop now. As you've seen, the two balls come down at markedly different speeds, and we'll have to analyze this more carefully to see if size makes a difference, but you see the point consistently. Heavier balls do actually fall faster than the lighter balls as long as they're the same diameter. The next object that we're going to drop will be a large watermelon and a small watermelon. Okay guys, get ready. Ready, drop, on cue. Now that had a rather spectacular end, but again you saw that they came down at different speeds. Again, we'll have to analyze it much more closely to be able to parcel out what's going on, but they did come down at different speeds. Okay, the next object that we're going to drop will be a large watermelon and a lemon. Okay guys, ready, ready, drop. That was interesting. It looks like the lemon actually came down faster. Okay, and finally the object will be dropped will be a large watermelon and a small cherry tomato, and we hope we'll be able to see the cherry tomato. Okay guys, you ready? Ready, ready, drop. And and again, quite a spectacular difference of velocity. Now, obviously, the ancient physics that Galileo was talking about, they had a point, and you can kind of get a feel for the obstacles that Galileo was facing. Here's very clear experimental evidence that indeed bodies that are different in size and maybe mass do actually fall at different rates. And so what we need to do is we need to look into the motions, the forces that govern falling bodies in some more detail so that we can explain this result and make it consistent with what Galileo himself found. So let's analyze these data. One of the problems with this experiment and with Galileo's is that things happen so quickly. The time of flight, if you can call it that, from the top of the building to the bottom is about 2 seconds. This means that small variations in things like time of release can produce large apparent changes in the outcome at the end. The trick is to analyze the motion so that these other things can be minimized. This is where modern technology comes to the rescue. Modern video cameras are essentially very fast still cameras, stringing together sequential images at a rate of about 30 frames per second. Our eyes can only process images at a rate of about 15 to 20 frames per second. This is why the faster sequences in a video clip appear to us as smooth motion. But with the appropriate technology, we can take these video clips and analyze them frame by frame so that we can follow motion to a resolution of about 33 milliseconds per frame. It's not perfect, but it's better than our eyes can do. And that is exactly what we're going to do. We will follow time of flight of our falling bodies and use our technology to correct for whatever complications we can. Let's start with our falling basketballs. As was evident at the time, the two balls were not dropped simultaneously. Taking a frame from our video clip, we can see this clearly and quantify the lag. The small basketball was dropped about 7 frames, about 234 milliseconds later than the big basketball. As we watch the balls fall, we freeze the frames as they fly past several landmarks on the building, and then on impact. We calculate the time of flight at each step and correct for the lag. At each freeze frame, we've overlaid the corrected times of flight. Let's watch this video again. You can see the flight of the two balls is very similar, but not quite. Specifically, the small basketball falls a little faster, about 67 milliseconds faster to be precise, than the large basketball does. What about the lacrosse and wiffle balls? Here, both balls were released simultaneously, but there was another complication as the wiffle ball hit an air conditioner on the way down. Thank heavens it wasn't a watermelon. For the frames we were able to capture time of flight data, the results are pretty clear. The light wiffle ball falls at a measurably slower speed than the heavier lacrosse ball. And now for the golf ball and practice golf ball. There was a slight lag in release time, but when we correct for that and measure the time of flight, we again see that the light practice ball falls considerably slower than the golf ball. I think we're beginning to see a pattern here. Now on to the fruit. Here, we're going to be dropping objects that have similar density but different diameters: large watermelon versus small watermelon, lemon, and cherry tomato. First, let's see what happens with the watermelons. Again, there was a slight delay in releasing the small melon, but correcting for that, we see a result satisfyingly close to what Galileo said we should find. Despite one weighing about half the other, there is virtually no difference in time of flight. What about the melon and the lemon? Here we see something very interesting. The lemon initially falls faster, but during the latter part of the flight, the larger melon catches up to it and both hit the ground at the same time. Very interesting indeed. And finally, what happens with the melon and the smaller cherry tomato? Here the results are clearer. The larger watermelon falls consistently faster, so the tomato hits the ground about 100 milliseconds later than the melon. So there are some interesting results here, certainly more varied than the simple idea that bodies always fall at the same rate, no matter what their mass or density. This doesn't mean that Galileo was wrong, of course, just that, to paraphrase Desi Arnaz, we've got some splainin' to do. What's different, of course, is that our bodies are falling through air, which has mass and therefore inertia, and viscosity and therefore friction. This means that gravity is not the only force acting on our falling bodies. Galileo had an inkling of this, and his genius was devising clever experiments, like rolling cannonballs down inclined planes to slow their motion, that minimize the effects of these other forces. In this course, though, we are actually interested in these complications, because that's where living things live. And as we saw, even when things are just falling out of the sky, the results can be complicated. Let's review. For objects that had similar density, we saw 4 results. The 2 watermelons fell at the same velocity, as Galileo said they should. The smaller basketball fell at a faster rate than the large basketball. The lemon fell faster than the watermelon initially, but the watermelon eventually caught up. And finally, the cherry tomato fell consistently slower than the watermelon. For objects of similar diameter but different density, we saw the same result. The lighter wiffle ball fell slower than the heavier lacrosse ball, and the lighter practice golf ball also fell slower than the heavier golf ball. Let's now try to make some sense of this. Let's look first at drag. The equation for drag force contains 4 quantities: the velocity, v, the density of the air, rho, the profile area of the falling object, a, in our case pi times the radius squared of our roughly spherical objects, and the drag coefficient, c sub d. We've introduced the drag coefficient in another video. Note how the drag coefficient is large at slow velocities, but tapers down to more or less constant values at high speeds. For most of our object's flights, drag coefficients will be in this flat area. More importantly, note how drag is smaller for bodies with a smaller profile area. This means that smaller bodies will experience less drag on their downward flight than large bodies will. This explains why the smaller basketball falls faster than the large basketball, and why the lemon falls faster, at least in the initial stage of its flight, than the large watermelon. But why does the tomato fall slower than the watermelon, or the heavier lacrosse and golf balls fall faster than the lighter wiffle ball or practice golf ball? Here the second concept, the terminal velocity, becomes important. First, let's explore what the terminal velocity is. Throughout the drop, gravity exerts a constant force on the object that happens to be the object's weight. Remember that a constant force produces a constant acceleration, and hence a constant increase of momentum. As the object falls, some of the momentum is transferred to the air. Remember also that transfer of momentum appears as force, which in this case is the drag. The important point to note is how the drag force increases with the velocity squared. As an object falls through a viscous fluid, initially it will be the force of gravity, that is the object's weight, that will dominate, and the object will accelerate at a constant rate. As it does so, however, transfer of momentum to the viscous fluid, that is the drag force, increases with the square of the velocity. There will therefore be some speed at which the gravitational force is exactly offset by the drag force. Here, there is no net transfer of momentum between the object and air, there is no net acceleration, and the body falls at a constant speed. This is the terminal velocity. This explains why objects of similar size but different weights fall at different rates. The forces on a lighter object will come to equilibrium at a slower speed than they would for a heavier object. This is why the wiffle ball falls slower than the lacrosse ball, and why the practice golf ball falls slower than the regulation golf ball. Every object falling through a viscous fluid like the atmosphere will attain a terminal velocity. The only question is at what speed this occurs, and this will depend in part upon weight and in part upon the viscous interaction of the body with the air. We can see this for objects of similar density but different sizes, that is, our falling fruits. Because both were quite large and heavy, neither of the watermelons reached terminal velocity before they hit the ground. Gravity was the larger force acting on them throughout the fall, and both hit the ground at the same time. If we had thrown them off a tall enough building, both would have reached terminal velocity, with the large melon falling slightly faster than the small melon. For the lemon versus melon, the lemon's overall lower drag resulted in a faster initial fall, but because the lemon was lighter, it reached terminal velocity about halfway through the fall. At this point, the melon, its motion still being accelerated by gravity, caught up with the lemon at the end. The same principle applies to the tomato, although it reached terminal velocity earlier in its fall than the lemon did. Because the melon continued to accelerate, it hit the ground sooner. So we had some interesting results here, and it's time for fruit salad.